Okay. Alright. Welcome to my EE320 lab final project. My name is Kenneth Buck, and my group is just me. Alright. So, for my project, I created a multitude of logic gates using 2N22222 transistors. A 2N22222 transistor is an NPN transistor that has 3 pins for a base, emitter, and collector. And they allow for basic logic functions to be carried out. And with these, I constructed these logic gates, so a NOT, AND, OR, and XOR, and technically a NAND, as you'll see later on, which serve as the building blocks for digital logic circuits. So, for example, the NOT gate is a single input, single output logic gate that inverts the input. So if you put in a logical 0, you get a logical 1 as your output. Conversely, a 1 goes in and comes out as a 0. The AND gate is a 2 input, 1 output logic gate, where the truth table is as follows, with 2 zeros being a 0, 0, 1 being a 0, 1, 0 also being a 0, and then 2 logical 1s combined together will make an output of 1. The NAND gate is the AND gate with an inverter at the back of it. So it does everything the AND gate does, but backwards, I suppose. The OR gate does kind of something similar, except the combinations where there's a 1 at all will yield a 1 output. So 0, 0, 0, 0, 1 is a 1, 1, 0 is also a 1, and then 1, 1 is a 1. NOR, OR with a NOT gate, is the opposite. XOR. So an XOR is created as follows, using 2 inputs, 2 logic gates here, and then a final logic gate here. So these first 2 are a NAND and OR gate, that NAND the A and B together, and then OR the A and B together, and then they're ANDed at the end here for a final yielded output. And when put in that arrangement, it'll yield this logic table, where 2 zeros makes a 0, 0, 1 is a 1, 1, 0 is also a 1, then 1, 1 is a 0. Kind of similar to the OR gate, not really. XNOR, XOR gate with a NOT gate. Okay. So let me go ahead and show you my schematics for the following gates. So we'll start out with the inverter since it's the most simple. It uses a singular 2N2222 transistor with a single input here, and then a VCC and an output. So, with a input of 1, we'll observe the out to be 9.739 millivolts, or a logical 0, and conversely, 0 volts shows basically 5 volts as our output, or a logical 1. The AND gate is 2 transistors in series, with 2 inputs going to each one, and V out being between this 180 ohm resistor and ground. Alright, so if I show this as 0, 0 to start out, then we see that this is also 0. 1, 0 is 0. 0, 1 is also 0. However, 2 5-volt inputs, or 2 logical 1s, makes a logical 1 output, as expected. OR gate is similar to the AND gate that uses 2 inputs and 1 output, except it uses 2 transistors in parallel. And we see here, starting out, I already had 0, 0 prepped, so 0, 0 going in as both my inputs for A and B gives V out to be 0. 0, 1 makes a logical 1 as my output. 1, 1 does the same, and I could show A is 1 and B is 0, but I think that's a little bit extra. So an XOR gate. An XOR gate, as you can see here, is a little bit bigger, because, as I showed before, it is created using the other logic gates. So, starting out, we know that the XOR needs to be a NAND, an OR, and an AND gate, which combines all the concepts of the 3 I made previously. So starting with the OR gate, we have that up here with the A and B inputs. Going in, I already showed off the OR gate, so I don't need to show it again. But that goes in, that output comes out to this input of the AND gate, or the first input of the AND gate. And then down here, we're combining the concepts of the and the NOT gate. So our Vout is going to be on top with a 10K resistor here between VCC and Vout, and then the two transistors in series here to serve as our AND portion of the NAND gate. It's basically just inverting the AND gate. That makes sense. And that serves as our second input for the final AND gate. And when ANDed together, we receive this Vout. So here I have 5 volts and 5 volts, or 1, 1, gives an output of 0. We'll do 0, 1. Oh, what's that? Huh, okay. It gives an output of 1. Oh, I see what I'm doing. Whoops. So 1, 0 gives us another output of 1, and then lastly we do 2 logical zeros. We receive a logical 0 as our output as well. So that follows the truth table right here as expected. Alright, so some of the last things I'm going to talk about are the problems I encountered. So starting with the AND gate, I didn't know what resistors to use. And that proved to be a bit of an issue, because I originally just threw in random numbers here. I thought a 10K would be okay. And it looks okay at first, until you do this combination, where your first input's a 0 and your second input's a 1. And that yields a 1 as our output, which, if we cross-reference our table here, wow, that's wrong. Huh. Okay. So I cross-referenced further, and I used a pretty reputable source that I probably shouldn't talk about, but I realized that my resistance value here was incorrect, and most of the designs I saw used a 180 ohm resistor. And once I put that in, that corrected my mistake, and I saw, boom, it's all of a sudden correct. Would you look at that? Another thing that kind of worried me was that I expected the Vouts to be 5 volts as well. And obviously they shouldn't, because there's a lot of voltage drop going across. But in the XOR gate specifically, say I set this to 5 volts. Our output's a logical 1. I saw that this was 3.39 volts. And I expected my answers to be closer to 5 volts, which this isn't. It's closer than, like, say 1 volt, but it's not quite where I wanted it to be. And I didn't know why. I was wondering if there's any other way to fix that, but I don't believe there is. But it should be okay, because this is a logic gate, so 3.39 volts, while it does have major voltage loss, it is still technically a logical 1. And for my final remarks, I just want to say that there's a whole different perspective seeing logic gates inside of this form, and then on a lower level on this form, using transistors. We always see these inside of our CPE classes, where, you know, it's an OR gate, duh. But when you look at an OR gate like this, where you see all the transistors, all the resistors with their corresponding values, and how everything would be wired up if it was zoomed in, then it brings like a different awareness to what you're really using. And you could go even further than this. For example, you could look at a resistor and say, what's a resistor? What's in it? You know, when we have it in the lab, we see this little plastic thing with 2 copper wires attached to the ends. Okay, cool. But what's in that little plastic thing? What makes that work? And so on. So that was just a little bit of extra tidbit of bit of a revelation I came to while making this whole project. One last remark I want to thank for my, I believe I have to give like an acknowledgement or something. Yeah, acknowledgements and references. I want to give an acknowledgement to Rojan Aslani, Alex Cater, I don't even know who that is, Grace Chi, I'm sure they're a great person. I actually do know this guy, Alex Contreras, pretty cool guy, and Ming Ju. Alright, thanks for listening. It was a good semester. I hope you have a great winter break.